Today we will be going over 1.3, the slope field. The key is still, if we know something like this, like before, what we can know is this is separable, and we can solve it analytically. And then, of course, we know this only works for the functions, ODEs, which are separable. But in general, it is not doable analytically. So can we do something else if we have encountered something that we don't know how to solve by hand? That is where we have the idea of slope field, or some people call it vector field, phase field, whatever, okay? Or direction field. So there are many, many names referring to the same thing. Okay. So basically, let's take an example of an ODE. Y prime equals 0.1 y. Okay. So what you have here is you have the relationship between your y and your y prime. That is, if you plug in a t and y in your equation, what you can do is actually you can have compute y prime using this function. For example, what will happen at 0 times 0 at y equals 0.1? Well, that is going to give you y prime equals 0.1 times 0.1, which is 0.01. I probably want to use 2 here to make it easier. So it's going to be y prime equals 2 times y, which is 0.2. Okay. What will happen at 1, 2? Where your t equals 1 and your y equals 2, then y prime is simply going to be 2 times 2, which is 4. Okay. So you can compute the derivatives at any given point. When I say point, I mean a point at t and y. So if you think about it, that is equivalent to say, if I focus on the ty plane, I can fix a point, okay, on the solution, and then I will be able to calculate the vector that at this point. It can be this, it can be that, it can be that. For example, the vector I have here at the 2.0, 0.1, let's do 2, 1 for me to draw, is going to be 2. It simply means if I find the point 0, 1, at here I'm going to have a vector. If I assign this to be 1, then this is going to be 2. So I will have this vector. That will be where my solution is pointing at. Okay. The vector you're looking for is 1, 2 at point 0, 1. For 1, 2, which is here, the vector you're looking for is going to be 1, 4, because you have a y prime equals 4. So you can easily draw a slope like that. Okay. What about other points? Well, given any points with a t and a y, because your y prime is going to be t and a y, what you are going to have is you are going to have all kinds of different directions. Okay. According to the ODE, somehow it will tell you the trend of where the solution is going next. Okay. So if you could do this kind of operation to calculate the derivative at multiple points and draw those kind of derivatives on the graph, you will be able to somehow to see the trend of the differential equation. So that's roughly the idea of the slope field. Now if you take a look, I'm going to solve y prime equals ky, a differential equation. I take k to be negative 0.1. So you know this one is going to decay, and this one is going to have a negative exponential function. Now if you draw all the vector field, like I said, okay, at one point you can compute y prime, at a different point you can compute y prime, you will be able to draw a direction field like this. Now starting from any kind of initial conditions, you can start to trace through these arrows to finally find out where your solution is going. This one is not going to be accurate, but so of course this one tells you the trend of where the solution is going. For example, it's going down. Second, the higher you start, the faster you go down. So it tells you a lot of information by just drawing the slope field, which is actually very easy, especially when you have a computer to help you to draw these. Okay? Now, of course, another question. When you draw things like this, you may have some difficulties. For example, if the derivative changes very much, at some point the derivative is going to give you 100, at some point the derivative is going to give you 0.1. If that happens, what will happen is not only this one is going to be flat, this one is going to be almost vertical. This one is going to be way longer because the vector is way bigger, but this one is way shorter. So what you will have is some vectors which tells you the difference between the direction, but also the difference in the magnitude. And if you put the same thing into the same coordinate system, it's going to be very hard for you to see. Okay, it's going to be just very, very. Let me, for example, let me say, if you make it dramatic, you will see some very long one and very short one at the same time. Okay, which is very hard for you to see. From here you can see you can barely see the ones on the bottom because they're just dots. Okay, so how do you handle this? Well, a simple way to do is, if I only care about the trend, how fast it is going, I will normalize everything. Okay, or just rescale. You can make the longer one to be shorter, and make the shorter one to be longer. Especially if you want to make them uniform length, then what you can do is some procedure called normalization. You simply take the vector and you make it a unit vector. That's it. Okay, so through computation you can easily do that. Okay, that is, you just divide by its own norm. Suddenly everything becomes the same length. Now you can see the trend clearly. Okay, now for the extreme case, like the one we did before with a negative, I think it's a 2. Now they are all of the same length. You can start to see, okay, where the trend is going without being disturbed by how long that vector is and how short that vector is, which is great. Okay, then how about you want to show these two information at the same time? Not only you want to show how long the vector is to tell you fast or slow decay growth. Meanwhile, you want the length do not disturb the trend because, you know, it can be hard to see the arrow. The one thing people will do is they will actually use colors to put another layer of information on what's going on. So for this one, for example, you already did this, okay? And then you try to normalize everything, but then you kind of lost, like, at which part is actually going really quick and at which going really fast, and then which part is actually just barely moving, even though the direction is going in an extreme case. What you can do is you can give them different colors according to the length. Okay. Now if you look at this graph we got here, everybody has the same length. Simply, it's easier for you to see the direction, but meanwhile, the one on the lower actually goes slower because it's, I don't know if you can see from the video, but it's shallower. And the one here is darker, which means, okay, even though the vector look identical to the length of what you have here, but it's technically a longer vector, so it's faster here. Okay. Another way to see this will be even more clear when you do logistics. Same idea. If you do this, let's see. Yeah, give me a second. I want to make it more dramatic. So you can see the difference. Okay, now it's pretty clear. Number one, you do have a lot of direction fields for the logistic, and you can see a solution of logistic, which is what we're familiar with, the S curve, actually follows the trend. Great. Second, you can see everything here is darker. Everything above is slow. Everything here is slow. So not only this one is going more flat, it's also growing slower. Okay, so the fastest growth about your derivatives is actually here. That's where you have the most dramatic derivative growth. So putting color and arrow together, it's very easy to see. Okay. This is where the most significant change happened. All right. The free diving examples we did before, we can also do the same thing. Okay, you can start to see, okay, if you normalize everything, the curve, I don't know if you guys did the exercise, but if you have, this will be the curve you are looking for. Remember the thing we drew last time? Eventually, you will receive a constant speed. Basically means, okay, your gravity and your air resistance balance each other. So your velocity stay unchanged because there is no force. Okay, to add color to it, simply add the line. Here, and then just put M here. We can add color to this graph. one more thing. Need to add the color map. Color equals red. CMP. Okay, from here you can see, okay, at first it's actually pretty dramatic how fast your velocity is changing, but at here your velocity barely change. Okay, so if you are going to track this particle, it's going to be really quick, and then slow down, slow down, slow down, slow down. All right, that basically is the idea of slope field. Especially with the help of computers now, if you are given any kind of ODE, no matter what you have here, of course, the first order ODE, you can always plug in a number, t and y. Okay. And then for each t and y, you can calculate the derivative. Therefore, you can draw a vector there. And you put all these kind of slopes together, you have a slope field. That will give you a lot of information about where your solution is going to go. Okay. Once you have that, the next thing you want to do is you want to pick up an initial condition. And follow the arrow, and keep following the arrow, and you will be able to trace down the whole trajectory of where the solution is going. That will be our basic for the next section, which is Euler's method. That is how to solve the derivative, and therefore how to solve the differential equations to find the actual solution using a computer. Okay. From here you can see that is basically how you get this dashed line. Okay. By following all the arrows you can follow. All right, that will be all for today.